Morning, everyone. The first speaker of the day is Ian. He's going to talk about Equivariant Rokhlin and Kappa Invariants of Seifert-Fibered Homology.
All right. Thanks for the introduction, and thank you to the organizers for the opportunity to speak today and the opportunity to visit Miami for the first time. So this outline might be a little too ambitious. See how it goes. But I think this talk is kind of like using equivariant index theory in order to say something about topology. And in particular, the first three parts of this talk, I guess the first 3 quarters will kind of be based solely off of like low text, like the equivariant two-finger index theorem, but it's inspired by certain interests in cyber written theory. And then maybe this last part has some gauge theory in it, and talk about how this all relates to invariants that I defined previously. So yeah, so maybe just to start off, I'll do a little refresher of Rokhlin invariants. All right, so recall that for Y integer homology 3-sphere. All right, we can define an invariant called Rokhlin invariant. Takes values in Z mod. Right, so how do we define this? Well, thank you. We'll take the spin filling W of Y, consider its signature divided by 8, and then consider that quantity modulant. And so here, W is any spin filling. All right, and we can show that this is independent of choice W, and in fact, it defines an invariant of homology components. All right, so we'll try it like this. It uses a homomorphism from the 3-dimensional integer homology coordinate group to Z mod 2. In fact, forget homomorphism because there exist homology 3 spheres, Rokhlin invariant 1. Okay. So this is a purely topological statement. I'm going to kind of now switch gears, fix a metric, talk about a related invariant. All right, so fix a metric E, and we'll define the following quantity. And with YG, what we do, we take spin filling again with choice of metric. Look at the index of the Dirac operator plus signature W. All right, so this is inherently a metric. Very maybe let me tell you some copies of it. Also work. And so this talk will call it the Seifert-Fibered floor correction term. And most importantly, for this talk, it shows up as the I'll just say the degree of the reducible solution in letter for least area cell down here. And it's also shown up in other places. So I'll just mention it. Where and also shows up. Land as one Equivariant and Saveliev. And maybe let me say a little bit about the properties of this concept. Also, is my writing okay? Is that too small? Okay. Okay, cool. So first thing is that this is kind of an integer lift of the Rokhlin variant, meaning that it reduces Rokhlin variant modulo 2. As you see that, well, we're working with the spin manifolds, dry operation, variant linear, particular x, Then we could say something about how it depends on the metric, right? So let's say I pick two metrics, B0 and B1, and look at the difference of these correction terms. All right, well, this is going to be equal to the spectral flow of the Dirac operator along a one-parameter family of any one-parameter family of metrics connecting G0 and G1. All right. In particular, the spectral flow, again, because it's quaternion linear, we're only going to jump by even numbers. And so you can imagine as you vary the metric, we're going to jump up and down by 2, but then modulo 2, we still reduces to the Rokhlin. All right, and then finally, it turns out this is independent of choice of spin. All right, so W, and let's say the metric that we chose for W. So I'll say a little bit say a little bit more about this last point. Are there any questions so far? Okay. Cool. So maybe I'll give a little proof of 3. And it basically follows from the Singer-Patodi index again for manifolds of boundary. All right, so I'll just state the following. All right, so I define this as the index of Dirac operator plus the signature of W over 8. And then by Patodi Singer, you can write it as the following linear combination of 8 invariants. So let me say a little bit more about it, not too much more. All right, so here, this is the reduced beta invariant of the Dirac operator. So it's just kind of small variation. I'm going to take 1/2 times the usual 8 invariant of the Dirac operator minus reduced beta invariant of the Dirac operator on a manifold. And then the second one is the 8 invariant for the odd signature. Okay. Those of you who've seen this before might be a little bit used by the signs, using current sign method in particular is opposite the one from APS. Trust me, it all works out. Okay, and so both of these guys only depend on the three manifold, and so that proves three.
What is the K of?
Oh, yeah, that's not standard. Dimension of the kernel.
Okay.
Yeah, maybe
It's what H.
Yeah, yeah.
All right.
Thank you, appreciate it. And then just one last remark. All right, so what I've written down, okay, it's a metric dependent invariant, but it actually gives you a homology before it's an invariant for specific things. And so particular NYG is a homology coordinate invariant when restricted to the class of homology Seifert-Fibered. All right, and I got like this is actually two independent proofs. It's back. Make like inclusion. So quality fair. All right, so here's the proofs. So one, I work with Ruberman and Saveliev. It's also equal to the Lorentz invariant and the Laurent invariant. Why? Yes. Oh, yes. Thank you. Sorry, yes. For G Seifert. Thank you. So by the Seifert metric, I mean technically it's a class of metrics, but it's not on that choice.
Like homology Seifert-Fibered space, what you need is Seifert-Fibered space with homology of this.
Yes. Okay, so Ruberman and Saveliev show that these are equal, and then by work of Saveliev, this is a homology coordinate invariant restricted to Seifert-Fibered spaces. Another way to see this is by work of operating. This is equal to minus the beta invariant line turned into Ford homology. And, let's say, the work of Malinowski, this is a homology conversion. Any questions? Cool. So, today I'm going to talk about equivariant refinements of both of these guys, the Rokhlin invariant and Saveliev polar correction term. Before we do that, I need to say a little bit about category of equivariant homologies here I've been considering. In particular, everything I've talked about, really depends on spin structure. Right? There's like a manifestly spin invariant. So when we talk about group actions or spin manifold, we want to get a group actions spin structure. So they'll just state series of definitions. All right, so let's say I have a diffeomorphism of my homology sphere of order some integer f greater than or equal to t. All right. Basically, we need to take a look at this thing. All right, so we say spin with sigma hat, sigma is lived on the nose. Spin lift sigma is linked to the principal spin free bundle. Which we wanted to double cover the induced action of this free bundle. Of course, really speaking as a free bundle, we can choose metric, doesn't have the full metric. Homology. All right, so that's all. All right, the funny thing about this is that when we lift sigma up to an action of the spinning bundle, we might not do order n anymore, right? We take upstairs, then power might be equal to -1. So we'll say sigma hat is even lift. This, yeah. The order was sigma hat is still n, and then call it an odd type spin lift if the order of sigma hat is kind of to okay, so basically we want to talk about cyclic group actions on homology spheres, kind of want to like remember this information and spin lift. So I'll let this pair y I'll make it Zn equivariant a spin integer homology. All right, spin is just remembering that we take into account this here. Sorry, can you say that again louder? Yeah, yeah. I'm not going to do this, but yeah, it's the existence of a spin lift is determined by a homological condition, and there's basically two choices of spin lift if they exist, and they're kind of related by the spin lift. Yeah. So, all right, similarly, we can define CM equivariant spin fillings. Homology coordisms. Et cetera, et cetera. All right, particular. Be a little hand wavy and say that you can find this all and define an equivariant homology coordinate group. Let's call it theta 3z spin c mod n. The funny thing about this is you need to be careful, right? We can't take connected sum as our addition operator anymore. Equivariant connected sums aren't always defined. There's a way to get around this using the notion of like a pseudo homology cobordism. This is all written down in Dihead and Malik's paper. But instead, we can just take the disjoint union as our addition operation, but you need to be a little bit careful about what that means. And I'm not going to. I'll just say we can find the Zn equivariant homology coordinate group. Rest is in the non-invariant case. All right, so, all right, once we're going to define equivariant refinements of Rokhlin invariant that gives an invariant of this group over here, as well as decided with the fourth correction term, we fix an equivariant measure. So in order to do that, I'm going to need to set some notation first. All right, so I'm going to let R of Z to M denote the complex representation right, of Z mod 2M. And this is the following presentation. It's just Z to join some variable C, modulo the relation C to the 2M minus 1. And what does this correspond to? It corresponds to the one-dimensional complex representation, where I send the generator Z mod 2M to E to the, say, 2 pi I. So this is a ring with addition given by direct sum, multiplication given by tensor product. We won't care too much about the multiplication structure of this guy. I'm also going to define a certain additive subgroup of this, the so-called symmetric representations of this. And it's just a set of polynomials in the CI. I goes from 0 to n minus 1. So this guy such that AI is equal to A to n minus 1. All right, so they're symmetric with respect to the conjugation. Also need to look at the real representation rank. Z mod 2M. Right, so it's generated by some classes of real representations, and we get the following representation. It's generated by the following variables: rho, mu1, all the way up to mu n minus 1, modulo some multiplicative relations which we don't care about. All right, what are those representations? Rho is just the one-dimensional sign representation. Then mu sub L is the two-dimensional irreducible representation, which sends the generator 1 to rotation by 2 pi over 2 pi L. You might ask why this doesn't go all the way up to 2n minus 1. Remember, we're talking about real representations. You can't do rotating this way over this way longer because those are isomorphic as real representations. Any questions so far? All right, so before I make the presentation, I'll tell you. All right, basically, we're going to find this equivariant Rokhlin invariant, and it's going to live in RO C mod 2M tensor T mod 2C. And the equivariance algorithm for correction term is again kind of like integer derivative. Oh, sorry. As mentioned, we are here. So you can check that as an additive group, RO real representation of Z mod 2M is isomorphic to that subgroup of symmetric function representations. And it's given by, so it sends rho to C to the N and UL to C to the L plus C to the 2N minus. Right, so that's the map given by the classification representations defines an isomorphism onto its atoms. Okay. So we'll kind of complete those two and switch back and forth whenever convenient. How am I doing? Okay. So the definition for the equivariant Rokhlin invariant is a little unwieldy. But I'll kind of go through it step by step. So first, remember, the non-equivariant one is just the signature of a spin filling divided by 8. We're going to take the following equivariant analog of this guy. So let's let Y sigma hat be a ZM equivariant spin integer homology 3 sphere. And we'll define it to be 1/8 times curly S W T tab hat. So I'll explain what this is in a second. Imagine. Take this mod 2. All right, where this is going to be a certain equivariant refinement of the signature, but is not the equivariant signature. It comes from really terms from the G spin. All right, so this is going to be what? Right, so I'll write it as this. Right, it decomposes along components. And it's going to be an element of RO Z mod 2M tensor irrational. Okay, so I can write any element of this as some of these following components. I'll just tell you what each of these guys are. All right, so S sub L is going to be the following.
It's T in folder and
Yeah, sorry, I should have written that. So Y sigma hat ZM equivariant. Oh, T, sorry. This is just the spin chunk. I just put that in the notation because it depends on tau hat is a lift of the ZM action to the spinner
there's
bundle.
a DMX W.
Yeah, yeah, and I'm taking equivariant spin. Sorry, I should have said that. Y sigma hat ZM equivariant homology free sphere, and then WT tau hat is a TM equivariant spin filling. Apologize to those of you sitting in the back. I know a question you're going to ask, but let me write this down and then I'll go into that. All right, so this one's kind of nasty. Let me just write it down and then I'll kind of say what all these terms mean. Got some cosines. Got some cosecants. And we also got some cotangents. Right. Okay. So that's the formula. Let me explain a little bit. Well, it's come from. So it's very interesting. So R invariant is the equivariant sigma. This is kind of like an equivariant index of graph. So there are a lot of like similar things, right? But it's inherently different. That's very good question. Yeah. And you know, those
But I don't know if that, they're different, but they still hold it.
maybe, yeah. Who knows? Let me say a little bit about where this all comes from. So the idea is that these terms, they involve the signature. Okay, but then we're kind of like perturbed by these extra terms involving a bunch of nasty trig sums. And these terms correspond to like the group action in tubular neighborhoods of like fixed point set of our. All right, so let's maybe just say a fixed point set of tau acting in our spin filling W. All right, and check because of the spin filling, fixed point sets are orientable and co-orientable. And so they have to just be leading points and surfaces. So let's say P1 through P sub. Sorry. Fix an initial K, look at the action of tau to the K W. We have some fixed points of this action, and then some fixed surfaces of this action. Sorry, let me just get my. Sigma K. So then K. And we have a bunch of fixed surfaces. Some of them might be contained in the interior, some of them might go out to the boundary. And on the boundary, we have a fixed top. Or fixed. Boundary. Okay. Around each of these fixed points, imagine this is a group action. It's going to act on the ball at a fixed point in 4 dimensions, and so we can always find an equivariant neighborhood where that action is determined by rotation about 2 different angles. Alpha, I, beta I up to some equivalence. And then around fixed surfaces, by rate of rotation, by a normal bundle, that's going to rotate by some angle psi theta. All right, so that's what we're taking all these trig functions of. And then all these epsilons here are just signs coming from G spin here, or the equivariant Cartesian index theorem applied to the Rokhlin, which depend on the subtle matter of geometry. Are there any questions about this? Yeah, yeah, I knew it was going to ask. So, yeah, so, the question was, does it exist? So, I proved in my last paper that the relevant force group equivariance in 3 manifolds is torsion. I believe that it's actually trivial, but I didn't know. So I was able to prove that it's torsion. And basically, we do this trick. Let's say y sigma hat didn't bound an equivariant spin manifold. I can just take n copies of that guy. Now that one I know has a spin filling for sufficiently many copies. I'll take this quantity and then divide it by how many copies it. Does that answer your question? Okay. Yeah, just use age as and show that it's origin. And yeah. Yeah.
You could also define it using adjective patterns here without knowing that there is an equivariant version.
Yeah, well, that's exactly what I'm saying. Yeah, any other questions, by the way? I know this thing is not. More days. Okay. So maybe let me give you some examples I can compute. As you can tell from the formula, what's harder to compute than not equivariant because we have to construct equivariant spin filling when I have complete knowledge of all 6.7. And then also those signs are very nice. All right, there's some examples where we can compute from the definition precisely. Okay, so maybe as a sanity check, let's like the following example. Look at the 3 sphere, and we'll let sigma sum n. Go. Like a 2 pi or n rotation just rotating right and back. Then for any choice experiment, the equivariant Rokhlin variant is going to be zero. So that's good. Nice sanity check. And so you kind of maybe think of S3 discrete actions, so kind of think of the second rank orders. Let's look at some more interesting actions on S3. All right, so let's fix P greater than equal to 2, Q greater than equals 1 to prime. And let's sigma PQ. Okay, that's sigma PQ. The usual CP action on S3, which realizes it as other line space. Okay. Then S3 discrete action. Then we have the following values of the Equivariant Rokhlin invariants. So I was just looking at P equals 7. So for 7, 1, and 7, 6. U S3, sigma hat PQ. So I chose a specific spin lift that I'm going to suppress. Equivariant Rokhlin invariant is equal to 8 sevenths plus 2 sevenths times mu2 minus 2 sevenths times mu4 minus 4 sevenths times modulo. So this you can basically just calculate from extending the group action to the ball with one fixed point, and then plug it into the definition, calculate it yourself. And then for 7-2, 7-3, 7-4, and 7-5, it's equal to 4 sevenths plus 2 sevenths U4 minus 4 sevenths U6. Okay, cool. So even for the simplest three-manifold 3-sphere, all right, with this cyclic group action, right, these equivariant Rokhlin invariants are non-trivial. And in particular, what's kind of nice about this example is 7-1 and 7-6 are L7-1 and L7-6 are homeomorphic, and the corresponding lens spaces to these guys are also homeomorphic, but these two classes are not homeomorphic, as can be shown by Reidemeister torsion. And so you kind of see like a shadow of this in this calculation. Is it equal to some invariants? Sure. Sorry, I don't have a better answer. Maybe, but off the top of my head, I don't know. I'm sure there's some relation. And there's probably some formula relating it to row invariants as well, but I haven't looked at that. Okay, cool. So great. We have some actions on S3, but maybe you want to look at some more complicated. So maybe briefly before I move on, I just want to make some remarks. Well, first, okay. I don't know if I wrote down proposition. Okay. this is an invariant of equivariant homology. I'll just say some uses. A holomorphism from theta 3z spin T mod n to R flow of T mod T n U over 2z. Okay, good. And then two, we can recover the ordinary invariant colors. And so mu of y sigma half is sent to mu y under the problem of homomorphism. Alright, so R is mod T n enter QZ 2z. Alright, we take the augmentation homomorphism on this first factor, which just sends the virtual representation to its rank. And make the identity that one, this goes to Z tensor T mod 2. Okay, so for these two reasons, I think this is a fair statement to say that this is the Equivariant Rokhlin variant.
I think you use coverage of the time.
I just so there are a couple of remarks. So first remark, this is a kind of subtlety here, but when I define this category for homology spheres, it's fixing generated, also fixing stimulus. If I change the choice of generator into stimulus, it actually uses an automorphism of R Z minus. So like it does change this invariant under prescribed way. Right. So in particular, maybe if I wanted to look at maybe the following more natural group, if I, taking this homology coordinate group and then maybe mod out by the, changing the choice of generator, choice of spin flip, Brandeis to the group, and then this homomorphism descends to a map to maybe on I'm talking potentially about that, but you can make this into a well-defined notion. All right, and then I'll even say what's asking about is okay, I've set everything in the context of integer homology spheres. You do the same thing for rational homology spheres. Take it towards the spin structure. So in particular, for an K, say S3, the 5 power piece of R. You can get coordinates ranks, follows where you can map K to the Equivariant Rokhlin variant of the PCR variant cover today with its unique equivariant spin structure and okay. Sorry, can you speak?
You have examples where you have either the kernel of the homomorphism or the specific homology that you have there that are not in the kernel, the equivariant.
Yeah, that would be great. I don't yeah. Okay, so, all right. I'm running out of time, so let me just say, all right, so analogously to how the Seifert-Fibered correction term is like an integer lift of Rokhlin invariant, you can define an equivariant correction term. And using Saveliev equivariant refinement, you can write it in terms of equivariant mean difference, the rank operator, plus some other terms. And turns out that we're able to explicitly use those for actions on homology Seifert-Fibered spaces. In particular, looking at the cyclic group action, looking at cyclic group actions, which are subgroup of the canonical S1 action on Seifert-Fibered spaces. All right, so let me write that down. The equivariant correction term. We can compute this for Seifert-Fibered homology spheres. Where we have the ZM action contained in the circle action. Acting on Y. And I'll end this talk with the application of this technology. Right, so N Y sigma hat G lies in R Z mod to N tensor Q and reduces mod to the equivariant Rokhlin invariant. And then the following. Population side. All right, so recently I worked of Mbari, Hamilton, and Braulio McMahon. They showed that following, so they showed that if we take let's say the group action Z mod N acting on reach-point sphere, homology reach-point sphere sigma, let's say ABC. This doesn't extend to any homology football, let's say, as a Z mod. Then it made that. Of course, lots of reach-point spheres don't count into your homology. Four balls, but some theory. All right, so in particular, We have some nice applications of this. Mark Hamilton, the Equivariant Rokhlin, probably have on Equivariant Seifert-Fibered Homology. All right, so now the question is, okay, it kind of says that these ones here, the group action are like non-zero in the equivariant strip homology, let's say. But what about the relation to each other? All right, so can we construct there being equivariant homology coordinates between sigma ABC hooked with sigma m actional plot rho by m for rotation, m-fold rotation fibers, and sigma A prime, B prime, C prime. In this model. So, so showing the papers, you could probably use the invariants and the topology developed by Mark Hamilton and their values. That's the problem. But wanted to maybe give a purely convex theoretic construction. All right, so we're going to consider this an example. Look at the family of least one spheres, sigma 2, 4n plus 1, n plus 3. Right, so this one, this family, 0 homology coordinates to it, and it's to passing error. And by calculating those equivariant correction terms, producing a module 2, Kappa Invariant. The following. So I'm going to look at the seed plant action on this family. In the cases where the Z type action is free, turns out that there's kind of a high periodicity to this. And for the computer program, then I was able to calculate this grand correction pair. And I get the following. So for this family, 2, 20n plus 9, 20n plus 11, so equals -2/5 and -1 plus 4/5 row, and the other two will be equal to 1/5 even cubed minus 2/5 row, and 1/5 even cubed minus 2/5. All right, so let's do this real group at the block invariant and the separate correction particular just by looking at these variants, I would produce these two are different, these two are different. So in particular, these two sets of energies are not the very following. So sorry, can you speak louder? Oh, exactly that actually being one day. C1 and oh, yeah, so one of the things here, so if you have a typical regression on baseboard theory, basically the other have to be in the case of involutions, the complex computation, or perhaps you can take in the circle acting up to conjugates. And so I could just say, let's say any homologically or any CMX I can go to is I can just say it's contained in the circle action up to this. And so that's what we're understand. There probably technologies here is like slightly more general to like fractional model or balls where this will find then. But yeah. What? Yeah. So the circle action doesn't extend over model. Sorry, I got yeah, in some cases we are, in some cases we are. Yeah, yeah.
What if you just take that to some invariant such that it's not a metric thing like equivariant, which is like something like using model one.
Yeah, I mean, yeah, I want to do that. So yeah. So maybe I'll say a little bit of speculation. Oh, thank you. All right, I think what Ali was saying is, why don't you lift this to a metric independent invariant using something like equivariant Seifert-Fibered homology. So in some sense, I didn't get a chance to talk about it, but can define these equivariant Kappa invariants using equivariant K theory, which are kind of like a metric independent lift of the correction term. And ideally, one should be able to define like a ROG graded version of equivariant monopole Seifert-Fibered homology, which such that this is the degree of the reducible, like the equivariant degree of the reducible in the ROG gradient. Does that answer your question? Okay.
Like you could also try to do the equivariant version equation, right? Now you can
Yeah, exactly. So I think that would be a great next project to define equivariant versions of alpha, beta, and gamma. Yeah, which should all reduce modulo 2 to this equivariant Rokhlin current that I defined.
Are there any other questions? Thank you.